All right.
Good luck.
Thank you.
Yeah, don't lose your gloves.
Sorry.
While we're on the subject, Laura. All right. Good morning, everybody. Welcome back to the final week of the semester. Hope you all had a good Thanksgiving break. Had time to relax a little bit before final madness ensues. Plan for today is I do have a quiz for you on Standard 20 as promised. And then we are going to begin Standard 21, our final standard on substitution method for integration. I've got my usual office hours of the next few days. Today and Wednesday at 11 and 2, tomorrow at 11 and 1. And as far as homework goes, I posted the final web work of the semester, homework 22, will be due Friday. Don't forget you also have one due tonight. And also, we're going to do something a little bit unusual. We're going to have a quiz Wednesday, even though I expect Standard 21 to take us 2 days to do. With the main reason being, if I wait until the class after we finish Standard 21 to give you a Standard 21 quiz, we're out of semester. There's no class days left that we could really do that in. And so the plan is, on Wednesday, we'll have a quiz only on what we cover from Standard 21 up to the end of class today. So Standard 21 is kind of going to be divided up. Today we're going to be mainly focusing on indefinite integrals, how we can use the substitution method. Wednesday we'll focus on definite integrals. And so the quiz on Standard 21 will be more focused on the first half. So then the exam question is likely going to be focused on this. Also, speaking of which, don't forget, class midterm on Friday. Every standard, 1 through 21. I think I've passed back all the retests I have. I haven't updated Canvas yet, but either later today or tomorrow, I'll update Canvas with everyone's mastery totals, so you know going into this exam what your mastery totals are. All right, I'm going to change the rules up slightly for this midterm. You know how normally I give you a sheet of notes going into the exam? Instead, I'm going to try seeing what happens if I take that sheet. No, I'm just kidding. You get 2 sheets of notes. 2 sheets, front and back, whatever you want written on it. I was planning on letting you do that for the final, and figure, might as well let you do that for this one as well. Any questions or comments before we get started for today? What is the best way to serve a pie in stats class? Best way to serve a pie is a la mode, because any other way is just too mean. Alrighty, and with that, go ahead and put everything away, because it is quiz time. Say what?
I said I'll take 2.
You take this for?
Probably not much better.
Don't be so sure.
right, we're gonna go.
Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Alrighty. Today is the end of an era. It's the last worksheet packet you're getting this semester. Anything else I pass out at this point in class is a quiz or an exam. Riley looks very excited at the thought of that. So today we're going to take a little bit of a detour and do a standard that's similar to what the first, third or so of Calc 2 course would look like. Where the first third or so of Calc 2 oftentimes ends up looking at what happens if we take an integral of something that looks really scary. Something with like different types of functions appearing in it, different sorts of pieces going on. And in other words, how can we integrate something that we can't just rely and say, oh, that looks like the integral, or oh, that looks like the derivative of this trig function, or oh, we can just use reverse power rule on this, or oh, it's a 1 over x, so it has an antiderivative of natural law. Turns out, real world, there's a lot of scary looking integrals out there where you can't just necessarily integrate using the techniques we've talked about so far. And I thought for our last standard, we would talk about one integration method, which is going to be called the substitution method, which you may have heard of before as something like U-Substitution or U-Sub, if you've taken a math course before. And we're going to talk about how you would go about integrating a function like this. Integral of 2x times square root of x squared plus 5. And what I'm going to do is I'm going to do a little bit of mathematical trickery, a little bit of sleight of hand, so to speak. And I'm going to rewrite this integral in terms of a new variable. I'm going to define a new variable, u, I'm going to set to be equal to x squared plus 5. And we'll talk in a few minutes about why am I choosing my new variable to be x squared plus 5 specifically. So we're introducing a new variable, u, which we could sort of think of as being both a variable as well as a function in terms of x. Given some value of x, if you want to find u, take square what you got and add 5 to it. If we were to differentiate x squared plus 5 with respect to x, Logan, what would that give us?
2x.
Yeah. So here I'm using Leibniz's notation for the derivative. Taking the derivative, in other words, you can think about this as sort of being u prime of x, so to speak. Except this time, remember how I said early on, when you see du dx like this, don't think about it as being a fraction. Today, I'm going to disregard my own command. We're going to treat du dx as being like a fraction. We'll talk about why that is here in just a minute. So, if du dx is just 2x, the derivative of u with respect to the variable x. If we multiply both sides by dx, whatever that is, that's going to give us this du term, which it should be equal to 2x times dx. And with that information in mind, I want to go up here now and rewrite our original integral. Except this time, instead of having x's in our integral, I'd like to have some way of taking everything that's inside of our integral and replacing it with this new variable u. So we want to replace everything that has x's in it with u's. Danielle, how could we take square root of x squared plus 5 and replace that with some expression that is u's instead of x's? Yeah. If u is x squared plus 5, then square root of x squared plus 5 should just be square root of u. So this term I'm going to be replacing with square root of u. And we still have a couple other terms in our integral that have x's in them. We have this 2x term and this dx term. How can we take our 2x and our dx and replace that with some stuff that involves the variable u instead of the variable x? Okay.
Could you replace the 2x with du over dx and then cancel out the dx's?
Ooh, okay. Just take this 2x right here and say that's a du dx term, and then we'll have a du dx times a dx, which just becomes du.
Sure. Yeah.
I like it. Alternatively, we could just say, hey, we have a 2x and a dx term that are sort of being multiplied here. We know that 2x times dx should just be equal to du. So I think we can actually just cut out the middleman. Say, replace both those terms at once with just a du term. Or we could totally do what you suggested as well and say we would end up with something like du dx square root of u times dx, and then these would cancel out and we can get to the same thing either way. Yeah, I'm on board. And if you notice, we've taken our original integral that was written in terms of the variable x, and now we've changed it into an integral that I hope is less scary of an integral, but now using everything's written in terms of u. It's like we're going from the language of x's and trying to take our integral and rewrite it in a whole new language, the language of u's. And so while we might be used to thinking about talking in English while we work with x's over here, now when we go to another language, we u. U to the 1/2 du. Cecilia?
What?
I just asked a question.
That's easy. Basic translation.
Sorry, I shouldn't be trying to. Sorry, I'm being mean to you.
Like just take the integral? Why am I blanking? Your language convoluted my brain.
My turn? Oh, it's integrated.
Go.
Oh, shoot, you want me to do it? Give me a second here. U to the 3/2 divided by 2 over 3.
No, divided by 3 over 2.
Ah, same difference.
Well, we have an indefinite draw.
Let's see.
Teamwork makes the dream work.
So, in terms of u, mocho, mokalichi, in terms of x. In terms of our original variable x. So in other words, what I just said using my gibberish U language, I was not actually saying anything, making random noises, is once we've written our original integral in terms of the variable u, we get an expression that looks a fair bit easier to integrate. Where Zach and Cecilia tag teamed after I picked on them a little bit. And that's something we could just integrate with respect to the variable u using the reverse power rule. Or we could write this as 2/3 u to the 3/2 plus c. Probably how I would write it. And we've taken an integral that's very scary to start with, changed our language from the language of x's to u's, back in terms of x, and now we've gotten an answer in terms of x to find something we couldn't have integrated otherwise. Yes, Rachel.
That's kind of late, but how did you get du dx equals 2x?
Oh, it's simple. I asked Logan and he did it for me. I don't know, Logan, why did you say du dx came out to 2x?
Because it's just what we've written with the power rule. It's 2 times the one that's on the x, and then the n minus 1
Oh.
Yeah, so in other words, I think he treated u as just a function of x. And then if we differentiate x squared plus 5, you think about it like as being f of x equals x squared plus 5, we would get f prime of x equals 2x. It's the same sort of idea going on here. Instead of f's and g's, we're using the language of u's. You know, the language of scuba debug. Dr. Ursel, what the heck did you just do? So this method, we're going to call the substitution method, or U-Substitution if you prefer. Mainly due to the fact that when we say substitution, we mean take our integral that was written in terms of one variable to start, and we're substituting in a new variable, which I know mathematicians tend to like to use u for this new variable, but honestly it doesn't matter, just don't use x again. And then once you write your original integral in terms of this new variable u, it becomes, if you pick a nice u and your problem is set up in a nice way, it's oftentimes much easier to integrate with respect to the new variable than it is to integrate with respect to the old variable x. Yeah, Josh?
How do you know which one's going to be u? Because like this one is pretty clear because 2x isn't that bad. But like what if you have something with like more in it? Can you like do multiple u's? Like substitute, could you actually use like u and then like a different variable?
Yes, that is standard 22,
Oh. I didn't have to do it.
i.e. Cop 2 standard 1. But yeah, we're not going to see any examples like that in this class of having to do a U-substitution, I think, inside of a U-substitution. There are such functions that exist. They're not particularly nice. Those are the sorts of integrals that I'd say we should leave for Dr. Gabler's functional analysis class. Yes, Rachel.
So what?
Actually, sorry. Before I answer your question, I forgot I didn't fully answer it. How did I know to pick u equals x squared plus 5? We're going to talk about that as we go forward with some more examples. Because with this one, I agree, it's maybe not so hard to see, oh, if we just let u be this expression inside the square root, then, hey, when we differentiate, we get everything that's outside of it. It won't always be that clear cut. And we'll come up with generally a strategy for how to do that as we go forward. Sorry about that, Rachel.
That answers my question, actually.
Ruby. So before I move on to the next page and start looking at another example, I want to answer the question of what the heck is going on here? Why does this method actually work? And to see why it works, I'm going to take this function right here, f of x equals 2/3 times x squared plus 5 to the 3/2 power. And I would like to see what happens if we differentiate this. So if we're looking at something like this, where we're not only taking like a polynomial, x squared plus 5, but after we take x squared plus 5, we're also plugging that into some other function, where we're taking that to the 3/2 power and then multiplying by 2/3. If we wanted to actually try and differentiate this, what differentiation technique would we have to use?
Chain rule and maybe product rule and chain rule.
I was gonna say, I think chain rule definitely, because we have
It's 2 over.
x squared plus 5 inside of a power. I don't think we'll necessarily need to use product rule to do that. I guess if you wanted to write this as 2/3 times square root of x squared plus 5 times square root of x squared plus 5 times square root of x squared plus 5, you could do a sort of triple product rule out of this. I hope you don't mind if I decide not to do that.
You're good.
Thank you. Yeah, we're gonna, actually, I'm not gonna call this F. Let's call this H. And you'll see why in a moment. Yeah, we could differentiate this using the chain rule. And then, of course, we'll have to use our constant multiple rule, power rule, etc. along the way. But I think the main rule that ends up needing to get used in order to differentiate this thing is using our good old friend, the chain rule. So if we want to use the chain rule here, we're going to need an inner function g of x and an outer function f of x in order to do it. Joseph, what would you choose to be your inner function here?
X squared plus 5.
Okay, and your outer function?
X to the 3 halves.
X to the 3 halves? How are you going to account for this 2/3?
What was it, 2/3?
Like that?
Yep.
Yeah. I would say that would be a good choice. That would make our h of x then equal to f of g of x, like we saw back in, oh gosh, what was the chain rule? Is that standard 7, I think? I think so. That would make it so our f of g of x would come out to our h of x here. So if we differentiated that, we would get f prime of g of x times g prime of x. I guess we need derivatives for f prime and g prime. Laura, what would our f prime of x be if f of x is 2/3 x to the 3 halves?
X to the 1/2.
Yeah, I think we'd get something like 6/6. That's a tongue twister right there, 6/6. X to the 1/2, which is just going to be x to the 1/2, or square root of x. Hannah, how about our g prime of x?
That would be 2x.
I like it. And now, if we plug everything into the chain rule, we'll take our f prime of g of x, which is square root of g of x times g prime of x is 2x. That's going to give us square root of x squared plus 5 times 2x. I'm going to write the 2x out in front because lo and behold, that was the original expression that we were trying to integrate. Avery. If I take a look at the left-hand board and how our U-Substitution method worked, I noticed that this g of x here, this x squared plus 5, kind of played an important role in what we did on the left-hand board. How is x squared plus 5 important in our integration approach?
That's what we decided u was.
Yeah, that's what we ended up setting our u to be equal to, was this x squared plus 5 term. And in fact, if we were to say rewrite this chain rule process to use the variable u instead of, say, g of x, we could have also said h prime of x is f prime of the variable u times g prime of x, so times du dx. Where here, I'm replacing g of x with u and g prime of x with du dx. sort of mixing my Newton and my Leibniz here a little bit for the sake of illustrating this. But then when we plug in f prime of u, that gives us the square root of u, or du dx was just this 2x term, and then when we plug in our u back in, we get square root of x squared plus 5 times 2x in the exact same way. So if you stop to think about it, this process of taking our scary looking integral, 2x square root of x squared plus 5, rewriting in terms of this variable u, integrating with respect to u, then plugging back in an x expression where our u's were originally. You can't leave your answer like this, by the way, because our original integral was in terms of x. Our final answer should be in terms of the same variable, x. And so essentially what we really just did here with our substitution method, we did the chain rule backwards. We sort of introduced a new variable u, which sort of took the place of what g of x would normally be when we did our chain rule. And then when we kind of rewrote everything in terms of u, the square root of u ended up becoming sort of our f of u, or our f of g of x if you prefer. And then once we integrated with respect to u, then we essentially sort of undid in our integration here what we would have to do here in order to differentiate this 2/3 times x squared plus 5 to the 3/2. We unraveled the chain rule in a sense. And so the reason why this works is ultimately because it's the chain rule, but backwards. So by rewriting in terms of a variable that makes your integral easier to compute, you're essentially doing this chain rule process in reverse. You're integrating something that would have taken the chain rule in order to differentiate in the first place. Josh, you were asking earlier, what happens if we have something like where we would have to replace multiple things with like variables, like a u and a v, so to speak? There's a rule in Calc 2 that you see called integration by parts, where that ends up happening, and what that is going to essentially be doing the product rule backwards. Yeah. So most of our derivative taking rules are going to in fact have integration rules, doing integration in reverse. I don't know about the quotient rule backwards. That one's a bit daunting. But like the chain rule, the product rule, just like how we have reverse power rule for the power rule, we have, we know how to differentiate an exponential, do the same thing in reverse to get an integration of an exponential. Almost all of our derivative taking techniques do have sort of integration variants to them. And this one is just how you would do the chain rule backwards. Any questions or comments before we move on to looking at a new example? Alrighty, in that case, I'm going to flip the page here. So I know you all are huge fans of trig functions. Let's do an example where we toss in a trig. Let's see what would happen if we tried to do integral of 4x cubed times cosine of x to the 4th. So to me, this looks scary because we have a cosine, which suggests to me that if we integrate, we probably want to have a sine term showing up, since the derivative of sine is cosine. But we can't, it's not as simple as just saying, oh, it's sine of x to the fourth, because we got this 4x cubed term showing up in there. And so I think we're going to need to try our substitution technique again in order to make this a little bit easier to work with. So we're going to need to introduce a new variable here, u, that would make it so just like how in the original problem, when we replaced our x's with u's, our integral was a lot easier to take. I'm going to do the same thing here. Find a way to translate our x's into u's in a way that makes our original integral a lot easier to find. Anybody have any ideas for what we could set our u to be? What?
X to the fourth.
You want to let u be x to the fourth? Why that?
Because when you take the derivative of u, you get 4x cubed dx.
In other words, you get some stuff that's already in the original integral. Interesting. So we could say du dx, as Wynn said, is going to be 4x cubed, which we just get from differentiating x to the fourth. That tells us that if we want to get a du term in there, we can replace 4x cubed times dx with a du. So these two terms will combine to give us our du. Tyra, how could we rewrite cosine of x to the fourth in terms of u? If u is x to the fourth, what would cosine of x to the fourth be?
Oh, cosine of u.
Yeah, I like it. We're going to have cosine of u. So once we make our replacements here, we'll have cosine of u du. Speaking of cartooning already, there's a language of u's. Now that we can carry out our indefinite integral, Emily. What would we get if we integrated cosine of u with respect to the variable u?
Sine.
Or sine of u? Or an indefinite integral, or plus our constant term. Dr. Gabler. Square is out front of that.
Kind of looks like sine of x to the fourth.
Ah! Dang it, you figured it out. Sine x to the fourth plus c. Now that we're back in our language of x's, we can say that our u has become x to the fourth. And now we can leave our answer in terms of the same variable that our integral started with, which was x. Rachel?
So the du always just like goes away whenever you integrate?
Yeah, it's the same reason that if I wanted to ask you, let's see, Rachel. What would we get if we integrated cosine of x with respect to x?
Sine of x. Plus c.
What happened to the dx?
It just goes away.
Yeah. Yeah, this dx term, which we're used to just kind of hanging out inside of our integrals the whole semester up to this point, it has a lot of kind of technical meaning later on in math, but for now I want you to think about this as being, this is telling you which variable, how do I put this in proper English? With respect to which variable you are integrating. So this says, x is the variable you're integrating with respect to, so cosine of x becomes sine of x. The same thing I would say up here is this, when we have our integral of blah, blah, blah du, the du term is giving us a signifier of saying, integrate this with respect to u. And so once we actually integrate to get from this step to that step, the du term kind of vanishes in the same way that when we integrate something with respect to x, the dx term vanishes once we actually integrate. Yeah, Laura?
So we have nice, okay, like the 4x to the third, that's kind of nice because it's the derivative of, the derivative of x to the fourth. What if it's not nice? Like what if that says 3x to the third?
Gadzooks. Then you would have something like what's going to happen in our next example. So I'll address that here in just a second. Good question. Yeah. No, I played nice to you on these first two, in that I gave you stuff where we could make our u terms, where you could choose a u that would make your du's happen to be exactly everything that's left inside of the integral. But you're right, Laura, that that's not always going to happen, and so we are going to have to address that by doing one extra step, which we'll see here in just a second. Good question, though. So like I was saying to Rachel, typically when we've been doing integrals before now in class, this dx is usually just kind of something that you just said, hey, just write it out. You have to write it after integral. Trust me, it has meaning. It's important. I'm not lying. Please believe me. But now, it actually ends up being pretty important when you're looking at integrals using a substitution method. And that in order to go from a dx to a du, saying integrate with respect to x versus integrate with respect to u, it actually is very important that you include it so that you have all the correct pieces going on here. Okay, Laura wants to see one where the u and the du dx stuff that turns out to not be quite so nice. So let's do an example of that. The one at the bottom of the second page ends up being another one that's fairly nice. So I'll leave that one as an exercise. Let's do this one. Integral of 2x squared plus x divided by 4x cubed plus 3x squared. A little bit scarier looking. And if you're convinced that U-substitution is the correct approach to take, sometimes it's not always going to be super obvious, like maybe it was for the first couple. What should be your U term? So sometimes you might just have to try a couple of different things first. Laura, since you asked the question earlier, give me something you would like to try to be our u here.
X squared.
U equals x squared? Okay. Let's see. So then in our numerator, we'll get 2u plus, what would x be?
Root x. Or root u.
Root u. Over something like 4u to the 3 halves plus 3u, and we still have a dx term here. We could take du dx, we get it's du equals 2x dx. Unfortunately, I don't think that's going to kind of get us to something that's easier to integrate it. It gives us another way to rewrite our initial integral, but not in a way that makes it any easier to evaluate, I would say. So I don't think that's going to be what we want to have our u be. I think our u is going to have to be something in it that has multiple pieces, multiple terms showing up. like how in our original integral we had x squared plus 5 as our u. Josh?
Could you set 4x cubed plus 3x squared to u?
Okay. And that would make our denominator just equal to u. Be nice if our numerator ended up then being something that's cool, handy to work with. What would our du dx be then?
12x, or 12x squared plus 6x.
So then our du would be 12x squared plus 6x dx. Unfortunately, we don't have a 12x squared plus 6x dx. We have a 2x squared plus x dx. This feels maybe similar to me, but doesn't quite work out.
Pull out 6.
Ooh, okay. So if we pull out a factor of 6, what are we going to be left with here?
2x squared plus x.
Like that? That's handy. I see a 2x squared plus x and a dx, which are kind of the missing pieces that we need to somehow get into du form. Problem is, though, we don't just have it. Our du isn't just 2x squared plus x dx. It's 6 times all of that.
And you divide it by 6.
Oh, divide both sides by 6? Like that?
Yep.
Interesting. That would give us 2x squared plus x dx, which is kind of everything that we still needed to convert from x's to u's. So Joseph, it sounds like to me, you're proposing that we take our 2x squared plus x dx and replace that not with a du, but with a 1/6 du. Like that? What do you all think? Is 1/6 divided by u, integrating with respect to u, look easier to do than our initial integral? Win certainly seems to think so. All right, Win, how would you integrate that?
Well, you can pull the 1/6 outside of the integral because it's constant. You can have 1 over u, basically your integral du, which would just be 1/6 ln of u plus c.
1/6 ln of, what was that, plus c?
ln of u,
Ln of just u?
absolute value of u.
Indeed. Yeah. Once we have an integral of 1 over u, which if you prefer you could write as u to the -1 power, that's something we know how to integrate. That's something we integrate not with the reverse power rule, because if we tried to use reverse power rule, we get, what, u to the 0 divided by 0? And don't divide by 0. But natural log of the absolute value instead. Riley, does that look good? Are we done? I don't think there's really anything simple, I don't know if I'd call, there's one thing I have in mind that I'd like to do still to this before I say we're done.
Plug in 4x cubed plus 3x squared for u.
Yeah, I think so. Since our original integral was written in terms of x, our final answer should also be in terms of the same variable x, I think. So we would get, what, 1/6 natural log 4x cubed plus 3x squared plus c. And I think that would be a good final answer in terms of x, just like our original integral. So Laura, to answer your question from earlier, what happens if you if your du dx ends up being something that's not quite what we have, but maybe a constant multiple of it, I think we would have to do like what Joseph suggested and say, well, we could divide both sides by 6 here to get a constant multiple of du is the stuff we have left, the 2x squared plus x dx. And once we do that, we could just replace that with not just du by itself, but a 1/6 du, or whatever constant multiple of du you have to work with. Because that constant 1/6 term doesn't end up mattering very much to the integral. As I was about to say, as Wynn suggested, but he seems to run out on me. As Wynn suggested, we could just pull that constant multiple 1/6 outside of our integral and just take 1/6 times the integral of whatever 1 over u comes out to be. Question. How can we check our answer and see that that is in fact the indefinite integral of 2x squared plus x over 4x cubed plus 3x squared? Other than going back through and looking at each integration step we did very carefully to make sure we didn't make any mistakes. Josh, what could we do to check our answer here?
Take the derivative of that, like by using the chain rule.
Yeah, and if we did everything correct, the derivative hopefully come out to be the expression we wanted to integrate to start with. So if we check, if we, let's say, differentiate it with respect to x, 1/6 natural log absolute value of 4x cubed plus 3x squared plus c. Don't worry, I'll do the hard part. Natural log of 4x cubed plus 3x squared. Well, derivative of natural log of blah, or even derivative of natural log of absolute value of blah, as we've seen, is going to be 1 over the blah, the stuff inside the natural log, times the derivative of what's inside the absolute value here. Which, when we write that out, is going to be, what, 1/6 times 1 over 4x cubed plus 3x squared times 12x squared plus 6x. And then we could multiply this term by 1/6 to kind of get rid of the hanging 1/6 out in front. So it'll give us 2x squared plus 1. And then we can combine these two terms. And lo and behold, 2x squared plus x. I know how to factor it. I know how to divide by 6. So divided by 4x cubed plus 3x squared. And I think our answer over here should be correct because the integral of that should be this, because the derivative of this turned out to be that. And in general, that's always a way you could go back and check your answer to any sort of integration problem, is try differentiating your answer and see if that gives you the same thing as what you started with. Are there questions or comments? Let's do one more. Let's set up one more. So everybody is on the same page. Let's do integral of x squared times square root of x cubed plus 1. Any ideas for what our u could be in this one? Any ideas outside of this front corner here? Yeah?
X cubed plus 1.
Okay. Let's see if that checks out. So if u is x cubed plus 1, Hannah, what would your du dx turn out to be?
3x squared.
3x squared. So that means du would be 3x squared dx. I see an x squared dx. I don't see a 3x squared dx though.
You have to factor out the 3 and then
Okay.
you divide both
I
sides by
factored out the 3.
it. And divide both sides by it.
Okay. So we would get just an x squared dx by itself would be 1/3 du.
Yes.
I like it. So then we could rewrite this as integral of 1/3 square root of u du. And then that would be 1/3 u to the 1/2, which would be 1/3 times 2/3 u to the 3/2 plus c, which would come out to 2/9 times x cubed plus 1 to the 3/2 plus c. Sorry, I went a little bit quickly because I want to make a couple more comments before I end class here. In general, with this U-Substitution method, I oftentimes think that the hardest part is trying to figure out what should your U be in the first place. In general, I think your U should, sometimes you'll just have to try multiple things, like we ended up doing over here. But in general, a good idea for your U is some expression that appears in the problem. In this case, like x cubed plus 1 appears inside of the integral, such that if we were to differentiate it, it would give us basically everything else inside the integral, or at least a constant multiple of everything else inside the integral. In this case, x cubed plus 1, if we differentiated, gave us everything outside of the square root, and then we just needed to multiply by 1/3 to account for the fact that we only have x squared dx rather than 3x squared dx. Okay, on Wednesday we'll talk about how to do this process with definite integrals, and I'll give you some time to work with your neighbors on a few practice problems in class. But just so you know, quiz on Wednesday, you can expect me to give you something that needs to be integrated using the substitution method. Hope you all have a good day. I will see you all on Wednesday. What's up, Wednesday?